Hi everyone, Mr. Parson here. So, you guys are on the Read Aloud, Think Aloud section of my website, meaning we're going to show you how I want you to think when you're working through some of the different articles or text selections that I'll give you throughout the semester. So the entire purpose of this video is to show you how I'm actually going to think when I read through a particular article, one of the ones that you will be reading very shortly. So, if you actually scroll down on this page, if you're on my website that is, watching this video, which I don't know where else you'd be if you're watching it, you will find the whole article, and it looks something like this. You guys can download it, and I would really recommend that you guys print it out because then you'll be able to follow along as we go through this video. So you'll be able to see how I would highlight certain areas or make annotations so that I can better relate all of this content and information to myself or to what I already know. One of the best ways to get through chemistry reading especially is to try and find ways to connect it or relate it to your experiences that you have already. You have a wealth of knowledge, why not use that to connect to some of the things that are more challenging? I think that it makes it a little bit easier to relate certain words and to connect some of these more ambiguous topics and concepts that we're going to cover to everyday things that you can easily relate to. So, this particular article that I've selected for us is called What is an Exothermic Reaction? And I got it off of scientificamerican.com, and it's written not as a super, technical science paper, but more written for people who are just curious or who want to read about what an exothermic reaction actually is. So, as I read through this, I'm going to try and make some connections to myself or just kind of point out different things that I'm thinking naturally as I actually read through this document. Okay? Make sure that you guys have a copy. Again, I think that's pretty important so that you guys can actually go through, see what I'm doing, and you can even make your own notes as we go along. Okay, so what is an exothermic reaction? We can all appreciate that water does not spontaneously boil at room temperature. Instead, we must heat it. Now, one of the things I think of immediately is, not spontaneously boiling at room temperature. I know that water boils, we've all boiled water, we've all made pasta or things like that, but if you've ever been up in the mountains, like up in Yosemite, one of my favorite places to go, when you boil things or when you're trying to do cooking, things boil at a lot easier, it seems to boil a lot easier. It just starts boiling a lot sooner than you would expect it to, but it takes longer to cook the food. So I think what that probably is it has to do with being at a higher elevation, and that changes how things boil. So just one of the things that I remember talking with my parents and things like that when we're camping in Yosemite. Because we must add heat, boiling water is a process that chemists call endothermic. Clearly, if some processes require heat, others must give off heat when they take place. These are known as exothermic. So that right there, both of those terms, exothermic and endothermic, you guys should know by now. We've actually gone over them in our textbook reading that we did last Tuesday. So one of the things that's kind of interesting though is how they present definitions in this case. In our textbook we've got bold word, and it gives you a very technical thing. An exothermic process is one that releases heat from the into the surroundings, from the system, blah blah blah. And here it was very very clear. It said must give off heat. That's exothermic. And that's all there is. So it's kind of interesting to see how different this does definitions compared to what we've already read and how we saw definitions initially. So continuing on with the reading. For purposes of this discussion, processes that require or give off heat will be limited to changes of state, known as phase changes, and changes in chemical constitution or chemical reactions. So we've already done each of these, right? With the phase changes, that makes me think when we did the lab where we did boil water. We took ice cubes, melted them, and then boiled the water. When we did that lab, we ended up getting that really weird graph that's angled, flat, and we discovered that there was phase energy, or energy that went into changing phase. So I think that's pretty much covers that. Chemical constitution, we haven't covered that yet, but we'll get there, don't worry. And chemical reactions, that is actually on the website already. You guys have your scientific claims you have to write. chemical reactions involve usually changes in energy. So that's how that connects to some of the other things that are going on in our class right now. Okay, so let's see. Changes of state involve a solid melting, a liquid freezing, a liquid boiling, or a gas condensing. When steam, which is gaseous water, condenses, heat is released. So there's not a lot of instances that we think of where steam is condensing, except there's a really easy one that we see every single day and probably don't even think about it. So I don't know about you, but I love taking really hot showers. It's the only way that I can wake up in the morning and get to class, and probably the only reason that I have a smile on my face. So if you ever see me and I'm grumpy, it probably means that Mr. Parson didn't get his shower in the morning like he wanted. So when I get out of my shower though, the mirror is completely covered in steam. Well, it's actually covered in what looks kind of like that foggy look to the mirror, so I have to like wipe it off before I can actually see, anything. So that's actually the steam that touched the cold mirror and it condensed on there. So it's actually releasing heat, and the place that it's dumping all of that heat is actually on the mirror. So that's one of the things that is every day that we see and don't even think of. Likewise, when liquid water freezes, heat is given off. In fact, heat must be continually removed from the freezing water or the freezing process will stop. That makes sense, right? If we take water out of the freezer, it's not going to turn into an ice cube anymore. We have to leave it in the freezer where it continues to take water out. Well, that doesn't make any sense. It takes energy out, not water. Our experience makes it easy for us to realize that to boil water or any liquid and thereby convert it into a gas, heat is required and the process is endothermic. In that one, what I would probably do is, if I had a highlighter with me, I'd underline that heat is required and endothermic, so that I know that whenever I'm talking about whether heat's required or being released, I know that it's required or there's some heat that needs to be put into the system for something that's endothermic. It is less intuitive to grasp that when a gas condenses to a liquid, heat is given off and the process is exothermic. And that's actually really true. I mean, it's less intuitive. It doesn't make sense that, we have steam and, coming off of our showers or whatever, and it has to lose energy before it can become the liquid water on our mirror. And we just don't even think about that. And it's just like, oh, well, the water was in the air, it has to stop, staying in the air. It doesn't just stay a gas forever, so it attaches itself to the mirror. And we don't think that it has to do with an energy, or the energy of our system, which is gaseous water. Alright, so on to the third paragraph. Perhaps it is easier to explain an exothermic phase change using the following argument. Liquid water had to have energy put into it to become steam, and the energy is not lost. Instead, it is retained by the gaseous water molecules. When these molecules condense to form liquid water again, the energy put into the system must be released. So that actually makes a lot of sense if we just keep going back to the shower analogy. Before we can have a hot shower, that water has to be heated up. So that's what our water heaters are for. We have, giant tanks, or if you guys have the ones that are instant heaters, then they're kind of smaller boxes. But they run water through them that's coming from, city water if you're, here in Fresno, or if you're out more in the country, then you guys might have a well. But regardless of where your water is coming from, it has to be heated up first, because coming out of the ground is not going to be that nice toasty temperature that you take your shower in. It's going to be freezing cold. So we have to put all of that energy in, and so at least with my water tank here in my apartment, I've got a gas tank, so it heats it up by actually just burning gas, and it's basically like boiling water on the stove, just not to the point where it's boiling, and it does it in a giant tube of water instead of a pot. And then for that steam, once it's in the bathroom, it has to lose all of that energy. It would make sense that it has to give it off before it's actually able to go onto our mirror. So when these molecules condense to form liquid water again, the energy put into the system must be released. I think I may have already read that sentence, but that's okay. It's still good to pick up where we left off. And this stored energy is let out as exothermic heat. The same argument can be made of the process of freezing. Energy is put into a liquid during melting, so freezing the liquid into a solid again returns the energy to the surroundings. So what I'm getting out of that is energy seems to always go in the direction of the colder thing. Energy seems to go from wherever there is more of it to less. And that kind of makes sense, right? If your hands are really, really cold or whatever, we put them on our neck or something that's warmer, your stomach, back, whatever, and I'm able to warm up my hands because the energy is going from my neck to my hands. So for my hands, they are gaining energy, so it must be endothermic, while my neck is being exothermic because it's releasing energy into its surroundings. So this is actually, I'm going to pause real quick. This is the kind of things that you want to think about, like what can I relate things to make these words make sense? Endothermic and exothermic, those are really weird words that we don't normally use, so you need to kind of attach those to something that you're more familiar with so that you can actually remember them and understand the concepts. Like phase changes, chemical reactions can occur with the application or release of heat. Those that require heat to occur are described as endothermic, and those that release heat are exothermic. So, I don't know if you guys have seen the most recent connection blog that I've just posted, but I was talking about how I like to bake. I really like baking. Well, one of the most essential parts of baking is throwing it into the oven to become, to actually be baked. And that requires a lot of heat. So anytime you're cooking or doing any kind of baking or anything like that you're doing in the kitchen, it's almost always an endothermic reaction, where it's going to have to put a whole lot of energy into it before you get what you want. Because having things like, raw chicken or uncooked brownies, well, okay, not uncooked brownies because the dough is really good to eat, but other things